Think about how a radio station, miles and miles away, can beam music right into your car. Seems like magic, right? Through thin air.
Or consider your phone's GPS. Pinpoint accuracy, guiding you somewhere new.
Exactly. What's the kind of invisible hand making these things work? And even, believe it or not, protecting us from space stuff.
Well, it's a region way, way up in Earth's atmosphere.
And today, we're diving deep into it.
Yeah, we are. We're taking a proper deep dive into Earth's ionosphere. We'll be drawing on, a lot of scientific understanding to show just why this seemingly far-off layer is so closely tied to our everyday lives.
The ionosphere, the name itself sounds energetic, doesn't it?
It really does.
And that's spot on. It stretches from, what, about 50 kilometers up to maybe 1,000 kilometers above us?
That's the range, yeah. And it's constantly being hit by radiation from the sun and from deeper space.
And this constant bombardment, this high energy hitting it, it does something pretty amazing, right? It knocks electrons loose from atoms and molecules up there.
That's the absolute key process, ionization. You end up with this, dynamic environment full of free electrons and positively charged ions.
So it's not just sitting there.
Oh, not at all. It's always changing, shifting. It's fascinated scientists for, decades now.
And that's exactly what we want to get into today. Our mission for this deep dive is to figure out the vital roles this ionized layer plays.
And maybe uncover some surprising ways it affects you listening right now every single day.
Right. We want to make it clear, get a good understanding, but without, drowning in super technical jargon. We know you want to get the key info quickly and thoroughly.
Absolutely.
So let's start right there. What exactly is the ionosphere? Maybe in a bit more detail.
Okay, so like we touched on, it's up in the higher parts of the atmosphere. It actually overlaps quite a bit with another layer called the thermosphere.
Okay.
But the crucial thing, the driver, is that intense ultraviolet, UV, and X-ray radiation coming off the sun. It just constantly bathes this whole region.
So it's like this part of the upper atmosphere is just permanently getting blasted with energy from the sun, causing these atoms to break apart, essentially.
Precisely. This continuous ionization creates this, sort of soup is a good way to think of it. Free electrons, positive ions, all mixed together.
Right.
Now, what's really interesting and kind of complex is that the concentration, the density of these free electrons isn't the same everywhere up there.
Ah, okay. So it varies.
It varies hugely, depends on your altitude, the time of day, obviously linked to sunlight,
Makes sense.
the season, and even how active the sun itself is being. Solar cycles, that sort of thing. Think of it like maybe a fog that gets thicker and thinner in different spots and at different times.
So it's definitely not just one simple uniform layer of charged stuff up there. It's got structure.
Absolutely. It's actually structured into distinct layers. Scientists label them D, E, and F.
D, E, and F.
Okay. And each one has its own properties, especially in how it interacts with things like radio waves.
Okay, so we've got a basic idea of what it is now. But the big question, the really important one, why should you, our listener, actually care about this region hundreds of kilometers up?
Well, despite being so far away, the ionosphere has this surprisingly direct impact on tech we use constantly, and even on our safety.
Okay, where do we start?
Let's start with something fundamental, radio communication.
Right, radio. How does this charged layer help us talk or listen to broadcasts across huge distances?
Okay, so certain radio waves, the ones in the high-frequency band, HF radio, think shortwave, some ham radio.
Gotcha.
They have this amazing property that can actually be reflected, bounced off the ionosphere.
Like skipping a stone on a lake.
That's a great analogy. Yeah, the ionosphere acts a bit like the water surface for these HF waves, and this reflection lets the signals travel way beyond the horizon, beyond the curve of the Earth.
Wow.
It's what enables intercontinental communication that just wouldn't be possible otherwise.
That's incredible. So without this atmospheric mirror, long-distance radio would basically be limited to like a straight line, point A to point B, if you can see it.
Pretty much, yeah. Line of sight. Without the ionosphere's reflective trick, long-distance radio as we know it just wouldn't work nearly as well.
Okay, that's huge. What else? You mentioned GPS.
Right. Let's shift to something you probably use almost every day. GPS, global positioning system, and similar satellite navigation systems.
My phone's map app is practically glued to my hand sometimes. How does the ionosphere play into that?
Well, think about it. Those signals from the GPS satellites way up in orbit, they have to travel through the ionosphere to get down to your phone or your car's receiver on the ground.
Ah, okay. They have to pass through that soup.
Exactly. And because, as we said, the density of electrons in that soup is always changing,
Right, it's dynamic.
those satellite signals can actually get delayed a bit, or even slightly distorted as they pass through all these charged particles.
Huh. So could that be why sometimes my GPS seems a little laggy? Or puts me just slightly off the road on the map?
It can definitely be a factor, yes. Understanding these changes, predicting them,
Mm-hmm.
it's absolutely vital for keeping satellite navigation accurate and reliable.
And that's not just for finding the nearest coffee shop, I assume.
Oh, definitely not. Think about aviation planes rely heavily on GPS, maritime navigation, ships at sea, even things like precision agriculture, where farmers use GPS for planting and harvesting.
Wow. So accuracy is critical there.
Absolutely. And significant disturbances in the ionosphere, maybe from a solar storm, they can potentially cause GPS errors of, well, several meters, which can be a really big deal in those applications.
Okay, that really drives home the importance.
Yeah.
So we've got radio comms, GPS nav. What other big roles does this layer play?
Well, it's also a pretty important shield, protection,
A shield? From what?
from the harsh radiation out in space. The ionosphere, along with Earth's magnetic field, they work together.
Ah, the magnetosphere.
Right. They help deflect and absorb a big chunk of harmful solar radiation and cosmic rays, high-energy particles that could otherwise reach the surface.
A natural sunscreen, basically.
Yeah.
But for really nasty stuff.
You could think of it that way, yeah. A crucial protective barrier we often just take for granted.
Definitely.
And one more thing, something visually spectacular. The auroras.
Oh, the northern and southern lights.
Yeah.
Breathtaking. What's the ionosphere's part in those?
So auroras happen when those energetic charged particles, mainly from the sun, manage to get funneled down by the magnetic field towards the poles.
Okay.
When they hit the upper atmosphere, they collide with the atoms and molecules within the ionosphere.
Right, that charged region.
Exactly. These collisions excite the atmospheric gases, making them glow. That's the light show. We see those beautiful dancing curtains of light near the poles. It's all happening up there in the ionosphere.
So the very same solar energy that can sometimes mess with our GPS
Yeah.
also gives us these incredible natural light displays. It's kind of a double-edged sword happening in the same place.
That's a great way to put it. A fascinating duality.
Okay, so we know it's super important now. Crucial, even. But when did scientists even figure out this layer existed? It's invisible, after all.
That's a good question. The first hints really came about because of radio back in the early 20th century, the 1920s mostly.
What did they notice?
Researchers, radio pioneers, they observed something puzzling. Radio signals seem to travel much, much farther at night than they did during the day.
Huh. That must have seemed really weird at the time. What did they think was going on?
It definitely sparked a lot of head-scratching and investigation. It led to this breakthrough idea. There must be something up in the atmosphere reflecting these radio waves.
The reflective layer.
Exactly. And crucially, they figured this something had to be influenced by the sun. The understanding gradually developed that during the day, the sunlight increases the ionization.
Creates more free electrons and ions.
Right, making the reflective layers stronger, or maybe creating layers that absorb certain signals. But then after sunset, especially in the lower parts of the ionosphere, the ionization would decrease because the sun was gone.
Okay.
And this dissipation, this weakening of the lower layers at night actually allowed radio waves to travel farther, bouncing off the higher, more persistent layers.
Wow, that's really counterintuitive. The lack of sunlight, in a way,
Wow.
helped long-distance radio back then.
It did for certain frequencies bouncing off higher layers. It showed how dynamic the whole system was. And this early work really set the stage for understanding that layered structure you mentioned, the D, E, and F layers.
Right, let's dig into those. Peel back the onion or the atmosphere layer by layer. Tell us about D, E, and F.
Okay, starting at the bottom, we have the D layer. It's the lowest part, roughly between, say, 50 and 90 kilometers up.
Lowest down.
And a key thing about the D layer is it's mainly a daytime phenomenon. The ionization that creates it needs direct sunlight, so it pretty much disappears very quickly after sunset.
Okay, so it's temporary. In a daily sense, what does it do?
Well, the D layer is known for absorbing radio waves, particularly in the medium frequency, MF, and high frequency HF ranges. So during the day, it can actually hinder long-distance communication on some of those bands.
So it's there when the sun's up, but it can sometimes get in the way of radio signals, a bit of a daytime blocker.
You could say that, yeah. It dampens certain signals. Now, moving up, you get to the E layer.
E layer.
Sometimes called the Kennelly Heaviside layer after the scientists who proposed it. It's roughly between 90 and 150 kilometers.
Okay, higher up. And this one?
This layer reflects HF radio waves quite well. It's really important for medium-range radio communication signals traveling, hundreds of kilometers, maybe 1,000 or so.
So the E layer is more consistently useful for bouncing signals, but maybe not quite intercontinental distances.
Generally, that's right. Then finally, you get to the F layer. This is the highest region, extending from about 150 kilometers all the way up to maybe the 1,000 kilometers or even more sometimes.
Way up there.
And it's the most heavily ionized region. This is the real workhorse for long-range, even global radio communication.
Ah, okay. This is the key one for that skipping stone effect over vast distances.
Exactly. And it does something interesting, too. During the daytime, the F layer often splits into two distinct sublayers. We call them F1 and F2.
F1 and F2. Why does it split?
It's related to the specific wavelengths of solar UV radiation being absorbed and the types of atoms and molecules present at different altitudes within that broader F region. The F2 layer is higher up and has the highest electron density overall.
So the F2 part is the most reflective.
That's right. It's crucial for those really long-distance paths. Then at night, the F1 layer tends to fade, and the F1 and F2 merge back into a single, broad F layer.
Fascinating. So it's this really dynamic F layer, especially F2 during the day, that lets radio signals hop across oceans and continents.
That's pretty much the story, yes. And of course, how we study all this complexity has come a very long way since just listening to how far radio signals traveled.
Oh, I bet. It's hard to imagine just relying on that now. What are the modern ways scientists actually probe the ionosphere? What tools do they use?
Well, we have a whole range of quite sophisticated techniques now. On the ground, we use instruments called ionosondes.
Ionosondes, what do they do?
They basically send pulses of radio waves straight up at different frequencies, and then they carefully listen for the reflections coming back down.
Like radar for the ionosphere.
Exactly like radar. By analyzing the time it takes for the pulses to return and which frequencies get reflected, scientists can build up a profile of the electron density at different heights.
Clever.
We also have much more powerful tools called incoherent scatter radars.
Yeah.
These are huge, very sensitive radar systems that can measure not just electron density, but also things like ion and electron temperatures and plasma drift speeds. Really detailed stuff.
Wow, that sounds serious. Are we also looking from space downwards?
Oh, absolutely. Satellite missions have been revolutionary. For example, NASA has the ICON mission, that's Ionospheric Connection Explorer. Its whole job is to study how weather lower down in our atmosphere interacts with the space environment right at that interface, focusing heavily on the ionosphere.
Interesting connection to lower weather, too.
Definitely. And the European Space Agency, ESA, has the SWARM mission. That's actually a constellation of 3 satellites.
3 of them.
Yeah, flying in formation. Their main job is to measure Earth's magnetic field with incredible precision. But doing that also gives them fantastic data on the ionosphere's structure, the currents flowing within it, and how it behaves globally.
So we're really getting this comprehensive picture now, looking up from the ground, looking down from space, multiple angles.
Exactly, a multifaceted view.
Now, you mentioned earlier this term space weather and that the ionosphere is a key part of it. Can you unpack that a bit more? What exactly is space weather and what's the ionosphere's role?
Sure. Space weather basically refers to the conditions out in space, especially conditions driven by the sun that can affect Earth and our technology, both in space and here on the ground.
So solar activity impacting us.
Pretty much. And the ionosphere often acts as the first point of contact or a critical medium for many of these space weather effects reaching Earth's vicinity.
How so?
Well, think about big events on the sun, like solar flares, these sudden, intense bursts of radiation,
Right.
or coronal mass ejections, CMEs, these giant eruptions of plasma and magnetic fields flung out from the sun.
Yeah, I've heard of those. Sound dramatic.
They are. And when the radiation or the charged particles from these events slam into Earth's upper atmosphere, they cause major disturbances in the ionosphere.
And these disturbances, these solar event impacts on the ionosphere, they have direct consequences for us down here. What kind of effects are we talking about?
Oh, definitely. These events can cause really rapid, really significant changes in the ionosphere's electron density and its whole structure.
Okay.
And that, in turn, can severely disrupt high-frequency radio communication. You can get complete radio blackouts over large areas.
Blackouts, wow.
And as we discussed with GPS, these ionospheric storms can introduce large errors and uncertainties into satellite navigation systems, making GPS unreliable just when you might need it most, perhaps during an emergency response.
That's a serious issue.
It can be. And in really extreme cases, very strong solar events can induce powerful electrical currents in the ionosphere, which can then induce currents in long conductors on the ground, like power lines.
Affecting the power grid.
Yes, potentially causing issues for power grids.
So just to be clear, a major eruption on the sun could potentially knock out important radio links, mess up GPS globally, and maybe even affect power systems, all because of how it stirs up the ionosphere.
That's the chain of events, precisely. And that's exactly why understanding how the ionosphere reacts to these solar outbursts is so incredibly important.
For prediction, I guess.
For prediction, absolutely. If we can model and forecast these disturbances, we can give warnings. We can develop strategies to mitigate the impacts, maybe reroute planes, adjust power grid operations, warn satellite operators. It's all about protecting our technology, which is increasingly vulnerable to space weather.
It really is quite humbling, isn't it, to think that the sun, millions of miles away, doing its thing, can directly influence our technology here on the ground, and this invisible layer, the ionosphere, is the crucial go-between.
It truly underscores how connected our planet is to the wider solar system. The ionosphere really is that critical interface layer.
Well, this has been absolutely fascinating, a real journey up into that dynamic region. Just to quickly recap the highlights.
Yeah, let's do that.
We've learned that this ionosphere, this layer ionized by the sun way above us, is absolutely vital for bouncing radio waves for long-distance communication.
Right. Couldn't do it the same way without it.
It plays a huge role in the accuracy or sometimes inaccuracy of your GPS and other satellite navigation.
A major factor in signal propagation.
It acts as this essential shield, helping protect us from harmful radiation from space.
Working with a magnetic field, yeah.
And it's the cosmic stage where those beautiful auroras perform their light show.
The collision zone for those energetic particles, it really covers a lot of ground, so to speak.
It really does. And amazing to think it all started with people noticing radio signals traveled further at night.
Yeah, from that simple observation to the complex science we have today. And the research definitely isn't over. We're constantly learning more about its intricate behavior, its connections to weather below and space above.
And its importance just keeps growing as our world gets more and more technologically interconnected, right?
Absolutely. Our reliance on systems affected by the ionosphere is only increasing.
Which really leaves you with a final thought, doesn't it? Considering how much we depend on technologies that this layer influences, what kinds of unexpected challenges or maybe even amazing new innovations might come out of studying this region even more closely?
That's a great point. The interplay between Earth's atmosphere, solar activity, and our global systems.
It's complex, and there's probably still a lot we don't know. Something definitely worth keeping in mind long after we finish this deep dive today.